All right, this is a review of homework 8. Question 14 said, for each of the following studies, say whether you would use a t-test for dependent means or a t-test for independent means. So here's the first one. A researcher measures the heights of 40 university students who are the firstborn in their families and compares the 15 who come from large families to the 25 who come from smaller families. This is a t-test for independent means because we have two groups of people. One group of people comes from large families, another group of people comes from smaller families, and there's only one measurement from each. We're getting the height from just each person. So independent means. Second one, a researcher tests performance on a math skills test of each of 250 individuals before and after they complete a one-day seminar on managing test anxiety. This is a t-test for dependent means. The reason is because we have two scores from each person. So we have a before score and an after score. So dependent means. And then C, a researcher compares the resting heart rate of 15 individuals who have been taking a particular drug to the resting heart rate of 48 other individuals who have not been taking the drug. This is a t-test for independent means, again, because we have two different groups, one group of people who have been taking a drug, another group of people who have not been taking a drug, and we're only taking one measurement from each person, which is their resting heart rate. All right, so number 17, a psychologist theorized that people can hear better when they have just eaten a large meal. I'm not aware of any psychological research that does this, by the way, so we'll just say that this is something that people are interested in. 6 individuals were randomly assigned to eat either a large meal or a small meal. After eating the meal, their hearing was tested. The hearing ability scores, in which high numbers indicate greater ability, are given in the following table, which I will present on the next slide. Using the 0.05 level, do the results support the psychologist theory? Use the steps of hypothesis testing and sketch the distributions involved. All right, so first, this is going to be a t-test for independent means because we have two groups of people. We've got the people that were assigned to eat a large meal, and we've got the people that were assigned to eat a small meal. And there's different people in each of these groups. And then we're taking one measurement, which is their hearing ability. So we're getting one score from each person. So 2 independent groups, 1 score from each person. So independent means t-test. All right. And here's the data in the following table. So we've got the big meal group. We've got 3 participants, their hearing scores. The small meal group, 3 participants, and their hearing scores. And so what we want to know is, on average, do we have hearing scores which are different in the big meal group and versus the small meal group? And not just different, I should say, the psychologists theorized that people can hear better when they have just eaten a large meal. So really, the hypothesis that we're testing is whether these scores are higher hearing scores. Okay, animation's messed up. All right, here we go. So I said population 1 big meal and population 2 small meal. That's kind of arbitrary, but so you could have, if you wanted to, said that population 1 was small meal and population 2 was big meal, but that's just the way I did it because big meal was presented first. So that made sense to me. It really only makes a difference when stating the inequality. So whatever you say is population 1, the inequality just needs to match. So because I've defined big meal as population 1, and because the hypothesis is that they should have better hearing scores, I'm specifying as the research hypothesis or the alternative hypothesis that mu1 should be greater than mu2. In other words, after eating a large meal, there should be better hearing scores, higher hearing scores, than after eating a small meal. So mu1 greater than mu2. And then the null hypothesis would be the opposite of that, which is that mu1 would be less than or equal to mu2. And again, if you reversed which was small meal and which was big meal, that's fine. Just reverse the direction of the inequality. So our comparison distribution. Our comparison distribution is a distribution of mean differences that is likely to occur if the null is true. And this can be somewhat of a mind bender to think about, but here's how we need to think about it. Let's imagine that there's no difference in hearing ability between eating a big meal and a small meal. So then what we're going to ask is what would happen if we took every possible random sample of size 3 from a population of people that ate a big meal, calculated their mean, and then we also took every possible random sample of size 3 from a population of people that ate a small meal and calculated their mean. Okay? Why size 3? Because we had a sample size of 3 in each of these groups. So there were 3 participants in the big meal group, and there was 3 participants in the small meal group. All right. So we're imagining, under the null hypothesis, there's no difference. You can think of the distribution of hearing scores in the population among, everybody that eats large meals versus small meals. There's basically overlapping distributions of hearing. It's like exactly the same. Okay. So we're going to take every possible sample of size 3 from the big meal group, every possible sample of size 3 from the small meal group, calculate their mean. All right. And so we get a distribution of means from both of these populations. Okay, so the large meal population has a distribution of means, and the small meal population also has a distribution of means. Then what we do is we're going to randomly sample from each of these distribution of means a mean. Okay, so then we're going to randomly sample a mean from the large meal group, we're going to randomly sample a mean from the small meal group, and then we're going to calculate the difference between these means. And we're going to put that in a pile. And then we're going to repeat the process over and over and over again. So the resulting distribution is a distribution of mean differences. Okay, so it's kind of an extra. With our other t-test, with our one sample t-test and the dependent means t-test, we only had kind of a single distribution of means. So now what we have is a single distribution of mean differences. You can think of a big pile of differences that we could calculate between the mean from the first group and the mean from the second group. So the resulting distribution of mean differences would be centered around a mean of 0. Why? Because under the null hypothesis, there should be no difference between these populations. And therefore, when we randomly sample means, over time, on average, we should get 0 difference between the means that we calculate. But we know sometimes we'll get a mean for the large meal group that will be somewhat bigger than a mean from a small meal group. So we'll get like a positive difference. And every so often, even if the null hypothesis is true, we'll get a mean from the small meal group that is larger than a mean from the large meal group. In which case, if we subtract mu1 minus mu2, or mean 1 minus mu2, we'll get a negative difference. Okay, so most of the differences will be 0, but we'll get some positive differences and some negative differences. So in other words, there's going to be a standard deviation of that distribution. Our job is to figure out what is that standard deviation. That is, just how big of a difference between means would we expect, just kind of due to random sampling error? Like what would be an average difference between means that we could expect? That's a standard error of the difference between means. And then the other thing that we'll know is that the shape of this comparison distribution will be shaped as a t-distribution based on 4 degrees of freedom. 4 degrees of freedom because we're just going to add the degrees of freedom from each of the corresponding groups or distribution of means from the previous group. So the large meal group had a sample size of 3. So n minus 1 is 2 degrees of freedom from this group. And then we also have n minus 1 equals 2 from the small meal group. So adding those together, degrees of freedom 2 and degrees of freedom 2, gives us degrees of freedom 4 for the distribution of mean differences. All right. So in order to determine the standard error of the mean difference, we need to determine several different things. We need to get an estimate of population variance, specifically a pooled estimate of population variance, and then we need to figure out the variance of the distribution of means for the large meal group, the variance of the distribution of means for the small meal group. We're going to add those together to get the variance of the distribution of mean differences, and then once we've got that, we can take the square root to get the standard error. So several calculations that we need to do. All right, so the first step is we're going to calculate the mean for both of our meal groups. So our big meal group, here's the average hearing ability, or the mean hearing ability is 24, which we just got by averaging 22, 25, and 25. For the small meal group, the mean hearing ability was 21, which we just got by averaging 19, 23, and 21. And then we can calculate the variance from these data. And we just do that doing our typical calculation that we've seen, where we just take our deviations, square those deviations, take the sum of the squared deviations, and then we're going to divide not by n, but by n minus 1. And doing so gives us an adjusted, unbiased estimate for the population variance. Okay, so based on our big meal group, we get an estimate of population variance that is 3. Based on our small meal group, we get an estimate of population variance that is 4. Okay, so we've done that. Now the next thing we're going to do is we're going to pool those estimates together. That is, we're going to take a weighted average of those two different estimates of population variance. Why do we do that? Because one of the assumptions of the t-test for independent means is that there's the same variance. In other words, the homogeneity of variance assumption, where the population variance is the same for both populations. And so if the variance is the same, what we're going to do is we're going to take a weighted average under the logic that each of these samples gives us an estimate of what that variance should be. So rather than using one or the other, we'll average them together to get the most stable and reliable estimate of what that population variance should be, because it's the same variance. It's the same amount of variance for both population 1 and population 2. So that's our pooled variance procedure. So we do that by taking a weighted average, where we essentially weight each estimate, so the estimate of population variance for population 1, the estimate of variance for population 2, we weight that by the proportion of the overall sample size that each sample constitutes. Okay, so essentially when we're taking degrees of freedom, that's just another way of thinking about sample size, really, because degrees of freedom is just n minus 1, so it reflects sample size. Okay, so what we're doing here is we're going to take estimate of population variance from group 1, estimate of population variance from group 2. We're going to weight that by the proportion of the overall sample that each group is. And so what you can see here is we've got degrees of freedom 1 is 3 minus 1, 2. Same thing, degrees of freedom 2, because n is 3, 3 minus 1 is also 2. Degrees of freedom total is degrees of freedom 1 plus degrees of freedom 2, so we get 4. And so we're just taking a weighted average of 3 and 4. Okay, so we're going to take those numbers and then finally add them together. So what you can see in this case, because when sample size is the same, taking a weighted average is you'll get the exact same number as if you would just take a simple average. Okay, so when sample size is the same, it can be a time-saving kind of step to just take the simple average of 3 and 4. Okay, that only works when sample size is exactly the same. When sample size is exactly the same, this weighting procedure is essentially redundant. You kind of don't need to do it because what you can see is that sample 1 is half or 50% of the overall sample, and sample 2 is half or 50% of the overall sample. So when sample size is exactly the same, you don't, strictly speaking, you don't need to do this weighting procedure. Okay, just taking the simple average of 3 and 4 will get you the same answer. Okay, so that's our pooled estimate of variance. With that pooled estimate of variance, we're going to use that to figure out the variance for each distribution of means. Okay, so for our first group, we take that pooled estimate of variance, divide by sample size from group 1. We use that same estimate of pooled variance, divide that by sample size of group 2. So the variance for the distribution of means for the large meal group is 3.5 divided by 3 is 1.17. And that's exactly the same for the small meal group because sample size was exactly the same. So calculations are pretty easy in this example because the numbers are the same. What we're going to do is we're going to take those two variances for each of the distribution of means, and we're going to add them together to get the variance of the distribution of mean differences. Okay, this is based on the variance sum law. Okay, so the variance sum law says we're going to take the variance from each of these distributions, add them together, and that gives us the variance of the distribution of mean differences. And then as a last step, we are going to take the square root of 2.34 to get the standard error of the difference. Now the standard error of the difference is nothing more than the standard deviation of that distribution of mean differences, and that tells us, on average, about how much should we expect any difference that we observe between two means to differ from the expected difference of 0 under the null hypothesis. So in other words, getting a difference between mean 1 and mean 2 that was 1.53 points on this hearing ability scale, that would not be unusual at all. That'd be like an average difference between two means that you would just get based on a random sampling process, even if the null hypothesis is still true. Okay, so we've just figured out the characteristics of the comparison distribution. We know that distribution of mean differences will be centered around 0. We'll have a standard deviation, aka standard error of 1.53, and that it will be t-shaped with degrees of freedom 4. Why? Because that's the total amount of degrees of freedom, adding up degrees of freedom from group 1 and degrees of freedom from group 2. So here's what that looks like. Next thing that we need to do is to determine a critical value. Recall that we had a directional hypothesis because we predicted that hearing ability would be better after a large meal. So that's a one-tailed test. We'll test it at the alpha level 0.05 that was given at the beginning of the problem. And then we have to use our lookup table, our t-table, and using degrees of freedom 4 as our total degrees of freedom. So doing that gives us a critical value or a cutoff score, whatever you want to call it, same thing, of positive 2.132. And so that's what our sketch should look like. So what we're going to be looking for when we actually calculate our actual t-value is for a t that exceeds, in other words, is larger than positive 2.132 in order to conclude that we have a statistically significant result. So step 4, that's where we're going to calculate what our actual t-score is. So we're going to figure out our sample's t-score, where our sample t-score lands in this comparison distribution. So to do that, our t-score is determined by taking the difference between mean 1 and mean 2 and dividing by the standard error of the difference. So we had previously calculated that the mean for the large meal group was 24. The mean for the small meal group was 21. We're going to take that mean difference and divide it by the standard error. So we get 3 divided by 1.53, which gives us a t of 1.96. Let's locate that in the comparison distribution, and what we can see is that it does not fall in the critical region. Our t-score did not exceed in magnitude in the expected direction our critical t, our cutoff score of 2.312. And so therefore, we're going to fail to reject the null hypothesis. Based on the data that we have from these 6 research participants, there's insufficient evidence to conclude that people who eat a big meal can hear better than people who eat a small meal. Okay, so it doesn't mean that the research hypothesis is necessarily wrong. It doesn't mean that there's not something to this theory. It just means that based on our particular study, we can't we don't have evidence for our research hypothesis, and therefore we have to fail to reject the null hypothesis. The difference between the means that was observed, 24 versus 21, that difference is not big enough to rule out that those 2 samples could not have been sampled from populations with identical means. Okay, so basically, in the strictest sense possible, what we're talking about is it could still be true that we get these 2 means of 24 and 21, and those 2 means, even though they're different, could have been sampled from populations that had identical means. We don't have enough evidence to rule that out. So right now, what we have to kind of accept, I guess, for the time being, is that people that eat a large meal and people that eat a small meal at a level of a population have the same hearing ability on average. Okay, we might not believe that in terms of the psychological theory, but we have to accept that in terms of what we have statistical evidence for or against. All right, number 18. 20 students were randomly assigned to an experimental group to receive an instructional program. 30 in a control group do not. What is this saying? All right, so 20 students got an instructional program and 30 people in a control group did not. After 6 months, both groups are tested on their knowledge. The experimental group has a mean of 38 on the test with an estimated population standard deviation of 3. Okay, that's nice. We don't have to actually go through the calculations of figuring that out. It's given to us. The control group has a mean of 35 with an estimated population standard deviation of 5. Using the 0.05 level, what should the experimenter conclude? Use the steps of hypothesis testing and sketch the distributions involved. Okay. Okay. So we've got population 1, people who get the instructional program, like the ones that were in this experimental group. Okay, so what we're interested in is a population of people, everybody in a population who would get this instructional program. And then population 2 would be people who do not get the instructional program. In other words, they would be like the control group. No particular effect was specified, whether there would be an increase or a decrease in test scores. So our alternative hypothesis is just that on average, the test scores are not the same. And our null hypothesis is that test scores would be equal. mu1 equal to mu2. All right, step 2 is to figure out the characteristics of a comparison distribution. I'll just go through this again just to really try to reinforce what we're talking about with this comparison distribution. Okay, again, it's thinking about this thought experiment. We're going to start by imagining that there's no effect of the instructional program. So in other words, the population of people that take the instructional program and the population of people that don't, they have the same mean on average, same test scores. So then we're going to ask what would happen if we took every possible random sample of size 20 from the population that gets the instruction, and then we take every possible random sample of size 30 from the other population that didn't get the instruction. Every time we take a sample, we calculate the means, and then we put them in a pile. Okay, so we form a distribution of means from each of the 2 different populations. Then we randomly sample from each of these distribution of means, and we calculate the difference between the means that we sampled. We do this over and over and over and over again, and we get a distribution of mean differences. We know that that distribution will be centered around a mean of 0. Its shape will be based on 48 degrees of freedom, which is the total number of degrees of freedom in our research study, 19 from the first group, 20 minus 1, and 29 from the second group, 30 minus 1. Okay. What we don't know and what we need to determine is what would the standard deviation, otherwise known as the standard error, be of this distribution. What we need to do is figure out the estimated population variance. Now, we were given in this problem what the estimated population standard deviation is. Isn't that right? The animation. Yes. We were given an estimated population standard deviation. Okay. So what we have to do is we have to take that estimated population standard deviation and square it to get an estimated population variance. We'll do that for both our experimental group that receives the instruction and our control group that doesn't. So squaring 3 gives us an estimated variance of 9, and squaring 5 gives us an estimated population variance of 25. We're then going to pool those estimates together. That is, we're going to take a weighted average. And taking a weighted average is important in this example because the sample size is different. So we have to give more weight to the sample that is the bigger sample. We're going to weight this estimate of population variance more because it comes from a bigger sample. Therefore, it should be a more accurate or reliable estimate of the population variance. So we're going to take a weighted average by multiplying each estimate of population variance by basically the proportion of the overall sample size that each sample is. Okay, so doing that, we've got 19 degrees of freedom for our first sample, 20 minus 1. We've got 29 degrees of freedom for our second sample, 30 minus 1. And then our degrees of freedom total is 48, which we just got by taking 19 plus 29. So dividing 19 by 48 and then multiplying by 9 gives us 3.6. Dividing 29 by 48 and then multiplying by 25 gives us 15. So I came up with a pooled estimate of variance that was 18.6, and some rounding error would be expected here just based on how you did your calculations. But if you're generally keeping 2 decimal places, you should have a number that is pretty close to 18.6. All right. And again, your estimate of pooled variance should always be between your two separate estimates. So you should not be getting a number that is lower than 9. You should not be getting a number that is greater than 25. It should be somewhere in between, as 18.6 is. Now that we've got that, we can use our pooled estimate of variance to figure out the variance for each distribution of means. Okay, so we'll do that for our experimental group, and we'll do that for our control group. It's important here that we had to take into account that we had 20 people in our experimental group, so the variance of that distribution of means is 0.93, and we had 30 people in our control group, so the variance of that distribution of means is 0.62. You'll notice that there's less variance in this distribution of means because it's based on a larger sample size. Okay, so generally, those means that are sampled will be closer together. Okay, next step is based on the variance sum law. We're going to add those two estimates together to get the variance of the distribution of mean differences. And then once we've done that, well, the animations are a little messed up, that's okay. We will take the square root to get the standard error of the difference. And this is ultimately what we need for our T formula. So it's a lot of work to ultimately get to the estimate of standard error. Okay, so now we've got all three characteristics of our comparison distribution. So we can sketch our diagram. We need to determine a critical value. We had set up a non-directional test, so we're going to use a two-tailed test, alpha 0.05 with 48 degrees of freedom. So we're going to need two values, positive cut score and a negative cut score. Now, in looking up the critical value in the t-table, what you will have noticed is that the table starts to skip degrees of freedom. So once it gets to like 30, it starts going goes in increments of 5. And so with degrees of freedom 48, we're somewhere in between 45 and 50 in this table. And so the default is we could say, okay, well, I could choose 2.014 or I could choose 2.009. The default is to use the higher of the values. That just makes it a more difficult or stringent cut score to surpass. So when in doubt, you make things more difficult on yourself. It should be noted that using a table is really not something that is commonly done anymore. We do have statistical software that will determine critical values and in fact actually tell us the exact probability of getting a particular result. So this is somewhat antiquated, but this is just to give you a sense kind of theoretically for how this stuff works. So before there were computers, there were statisticians that came up with this methodology. And so if you understand this methodology, one day you can use a statistical software program. Okay, so, right. We've got our positive and negative 2.014 as our critical values. What we now need to do, did I skip a step? I guess I didn't calculate the, t-score. Well, that's unfortunate. Well, how would we have gotten there? All the animations. Great. Okay. So we're taking, the experimental group had a mean of 38, and the control group had a mean of 35. So the top of our t formula is going to be 38 minus 35. And then we're going to divide that. Okay, so we got basically 38 minus 35 is 3. We're going to divide that by the standard error that we calculated, which was 1.24. So we've got 3 divided by 1.24 is going to give you a t of 2.42. So that t of 2.42 falls in our critical region. And so we are going to decide to reject the null hypothesis. We do have a statistically significant result. And our conclusion would be that it appears as though the instructional program is effective at increasing knowledge. Typo there. All right. All right, so that's it for the homework. Hopefully you found that review helpful. Thanks.